Good evening, everyone. Welcome to the fourth live session of mine for the course Design of Reinforced Concrete Structures offered by NPTEL. I am Arshit Agrawal, PMRF Research Scholar from IIT Bombay, and I will conduct weekly live session for 12 weeks for this course. So, just to start with, what is this session all about? So these are weekly interactive session which happens every Tuesday from 6 p.m. to 8 a.m., 8 p.m. till the course runs. How do we interact? We interact by answering the questions that I have asked in the chat box, or by posting your queries in the chat box, or by raising hand, unmute and asking your queries. Apart from the class, you can also always clarify your doubts by going to the discussion forum of the course, where the questions will be addressed in the discussion forum itself or in the next live session. And these live sessions will help you to answer the graded assignments easily and will help you to develop further understanding about the topics. So I hope everyone are clear about the session. Now, in today's session, we will first have a look of what we discussed in the last live session that was for week 3 of this course. Just a quick glance. Then we'll discuss week 4 content, starting with a quick overview of design of flanged section. Then we'll see a numerical on flanged section. After that, we'll start our discussion over limit state of collapse in shear. We will first discuss basics of flexure and shear failure, how stirrups are considered, and how designing of shear reinforcement is done. In today's class, we will see around 4 to 5 numericals, since that will provide you a better clarity of applying the codal provisions. And finally, we will conclude the week. So, in the last live session of mine, we first talked about limit state of collapse and flexure, where we went through a discussion upon how singly reinforced beam is designed. We looked at stress versus strain plot, material behavior, derivation of relations, and one numerical. We then talked about design versus analysis. So, design is done when we know the external load and moment acting on a section, and we want to design for depth of section and area reinforcing area required. And while analysis is done when we know all the parameters of a section and we want to calculate what is the moment capacity of the section. Then we talked about doubly reinforced beam when it is needed, when the moment acting on the beam is more than the limiting moment or the balanced moment of the beam, such that additional reinforcement is needed in compression side to balance the extra moment. We saw the stress strain plot, how to go along with solving such cases, and a numerical related to it. And finally, we discussed about flanged sections. What are those? What are different cases in terms of design in flanged sections and a general flow of design? Okay, so just to recap the last part before looking into a numerical. So, what are flange section? These are the section which are formed by a combination of two or more individual components. So, you can see in the first image, it is a L beam which is formed due to the interaction of a column and a beam at the external joint. Okay, and the second image shows you a T beam which is formed due to an interaction of a slab and a beam. Okay, now based on stress block, flange section design can be divided into three cases. Case 1, when the neutral axis lies within the flange. Case 2, when the neutral axis lie below the flange but the flange is uniformly stressed. And case 3, when the neutral axis lies below the flange and the flange is not uniformly stressed. Now, how to judge which of these cases we need to deal with? We get that judgment by getting the value of x, the depth of neutral axis, df, and d. Okay, so assuming Fe415 grade steel, for now, we can calculate df by d value by using similar triangle property, and just clubbing everything about and based on this df by d value and x value, we can judge which case we are belonging to. Okay, so just to club everything that we discussed about flange section in the last session, how we analyze, we first get the parameters. These are the parameters that is generally given to us in the question about a flange section. Okay. Now we calculate x by assuming tensile failure and equating the forces of compression force and tensile force. We equate and we can get the value of x. We compare x by df. So if my x is less than df, it means that my neutral axis is lying within the flange. So it is case one of design. So I can calculate mu by considering both steel and concrete failure, and the lower value of which I will take as the limiting value. If my x is greater than df, it means that my neutral axis is lying out of the flange. So I need to calculate the df by d value. If my df by d is less than 2, it means that my flange is uniformly stressed. So I will go on with the case 2 of design that we saw in the last week. And if my df by d is greater than zero point 0.2, I will go with the case 3 of design again, which we saw in the last week how we design. Okay. So since it is now clear about how flange section is designed, we will look at one numerical. So what this numerical says, the figure shows a cross section of a continuous T beam. The cross section dimensions are fixed by considering hogging moment as support. The effective flange with BF is calculated as 1400. Determine the area of steel required to resist a sagging moment of 650 kilonewton meter at midspan. Assume moderate exposure condition. Grade of steel is Fe415. So I will wait for a couple of minutes for you guys to try to solve this problem on your own, and then I will discuss. So you can see in this problem, some of the parameters are given to you, some are not given to you. So you need to see the additional information that is given, like moderate exposure conditions and everything. And sometimes you need to start with some assumptions when you don't know how to proceed. So try to solve, else we will discuss. Okay, so let's see the solution now. So first, what all things are given? So the given data includes, we know BF is 1400 mm. We know DF, depth of flange is 100 mm. We know BW is 300 mm, and we know total depth B is 700 mm. Okay, and mu, which is acting, it is 650 kilonewton meter. Okay, so what is the first step? We also know Fe415 steel is used. Okay, now what are the things that are missing to us right now? The value of D small d effective that we need to calculate, and what is the grade of concrete. These two values are first that we need to determine. So since it is given in the question that it is moderate exposure condition, so if you will look into IS 456, IS 456 says that for moderate exposure condition, minimum grade of concrete that needs to be used is M25 grade, and the depth should be more than 30 mm. So let's assume a cover should be more than 30 mm. So let's assume a cover of clear cover of 40 mm in our case. Okay. So if we now calculate D, so small d will be, small d now will be 700 minus 40 minus, let's assume we will provide 20 mm dia rebars. Okay, so let's fix the diameter of the rebars also that we will provide. Okay, so our effective depth will come out to be 650 mm. Now how we'll proceed? Let's assume that our neutral axis, that let's assume that x is less than df. Since we don't know which case we are belonging to right now, so we need to start with an assumption. So let's assume that our x is less than df. This means that we are belonging to case 1 of design. Okay, case 1 of flange section design. Now how to solve this? So we know formula mu is equal to 0.36 fck x d minus 0.42 x times df. So we know the value of df, we know the value of fck, we know the value of d, and we know the value of mu. So we can calculate the value of x. Now if this calculated x will come out to be less than df, then this means that our assumption is true and we can proceed ahead with the calculation. If x comes out to be more than df, then this means that the numerical doesn't belong to case 1 of design, and we need to check for case 2 and case 3. Okay, so just substitute the value. So 650 into 10 to the power 6 is equal to 0.36 into 25 into x into 650 minus 0.42x 4 into 1400. So just try to solve this. So upon solving, you will get two values of x. Okay, since it's a quadratic equation, you will get two values of x. One value will be 83.86 millimeter, and the other value will be more than 1500 mm, which is practically not possible. Since our total depth is only 650 mm, this value is can be discarded. Okay, so this value will discard, and we will take x as 83.386 mm, which is less than df. This means that we belong to case 1 of design only. Okay, now since I know the value of x, what I can do, I can use direct relationship. X by d is equal to 0.87 Fy AST upon 0.36 FCK df. Now here we know x, now we know d, we know Fy, we know FCK, we know bf. So AST can be calculated easily. So just substitute the value and you will get AST equal to 2926.38 mm square. Okay. Now we assumed diameter of dia of 20 mm. So the number of rebars required will be total area AST upon area of one reinforcement. Area of one rebar. So when you will do this division, you will get around 9.17. So we can say we can say round it up to 10 number of rebars. So the total area that we will providing will be more than sufficient. Okay. So this is how we will solve this question. So we have determined the area of steel required and the number of rebars that we need to provide. Okay. So what we did first, we for moderate exposure condition, we estimated what grade of concrete and cover we need to go for. Then we calculated the effective depth. Once we calculated the effective depth, we assumed that our neutral axis is lying within the flange. So for using that, we calculated the depth of neutral axis. We observed that the depth of neutral axis is actually lying within the flange. So our assumption is true. So once our assumption is true, by equating the forces, we calculated the area of steel required. And since we know the diameter of rebar that we are going to provide, we calculated the number of rebars. So this is how design of flange section is done. Clear? Okay, so let's proceed ahead now. So till now we have talked about limit state of method. In limit state of method, till now we have talked about flexural failure. Now we will talk about another kind of failure that is known as shear failure. So, in reinforced concrete, failure can be classified into two types: flexural failure and shear failure. Flexural failure occurs when the load on a beam or any cross section exceeds the flexural capacity, or we can say bending capacity of the section. Okay, this kind of failure can be further classified into two types. First is flexural failure under tension, where which is our under reinforced design case, where steel yields before concrete. And the same can be seen in the image also, how concrete cracking is appearing at the bottom due to yielding of steel reinforcement. And the second case is flexural failure in compression, in which is our over reinforced design, where concrete yield first before steel. And the same can be seen in the image as to how blistering of concrete is happening at the compression site. Okay, so these are the two cases of flexural failure that we generally talk about. Now the second form of failure is failure due to shearing force, which occurs when the shear force exceeds the shear capacity of different materials of the beam. Okay. Now, what is shear force? A shear force is a force that tends to produce a sliding failure on the material along the plane that is parallel to the direction of force. So, just to better understand this statement, suppose we have a beam under a single point load. Okay, so this beam will experience bending. Now, along the depth of the section, my bending value will be different. So here my bending will be maximum, here bending will be minimum. And that will be governed by the strain at a particular depth. So if we assume this as pure concrete, not reinforced concrete, so this I am assuming as pure concrete. So my strain profile will look like something like this. And since we assume from our assumption that the plane section will remain plane even after bending, and my bending profile also in this case will appear like this only. Since I am assuming pure concrete, I am assuming that the concrete is also taking tension. So you can see how the bending moment is changing along the depth of the section. Okay, now the bending will be maximum at the top and at the bottom, and minimum at the mid span. But opposite to this, my shear force at any section is defined as equal to the rate of change of bending moment. So now if I see the variation of shear force, my shear force will variation will look something like this. So it will be maximum at the center and minimum at the ends. So now this variation shear force along the direction of force action is what produces the shear stress in the material, which when exceeds the shear strength of the material leads to failure. Okay, so what happens when shear stress exceed the shear stress acting on the material exceeds the shear strength? So there can be three kinds of failure. Okay. Now, what are these three failures? First is the diagonal failure, where the crack will first initiate from the tension zone and it will slowly propagate up to the compression part, and this is a like a kind of a development of vertical crack at the bottom due to tensile stresses. Second kind of failure can be termed as diagonal compression failure, where there will be crushing of concrete at the tip of the diagonal crack around the area of point of load application. And third is true shear failure, which will happen near the support, so where the diagonal stresses develop due to the which transfer of load will happen near the support and at the point of load application. So these are the three cases in which shear failure can happen. Now, how to mitigate these failures? By providing reinforcement which can arrest these diagonal cracking, and this is done by using stirrups. So these can also be placed into three different types. Okay, so we have vertical stirrups, which can be single legged, double legged, four legged, and six legged. So basically, these are the stirrups that will be resisting the diagonal cracking. Okay, so why I'm saying two legs? Because there are two stirrups here which can resist the diagonal crackings. Similarly, here there are six stirrups to resist the diagonal cracking. Here there are four stirrups to resist the diagonal cracking. Okay, so vertical stirrups are the ones that run perpendicular to the longitudinal reinforcement, having two functions. They have two functions. Okay, so first function is to hold the longitudinal rebar in position, and second function is to arrest the shear by opposite steel members. So these are the opposite steel members by which it can arrest the shear. Okay, so this is the first form of shear. Second can be by providing inclined stirrups. So by providing inclined stirrup also we can resist the cracks. Okay, and third form is by bending the longitudinal rebar near the edges. Okay, so by this also we can resist the cracking that is happening. Now this is the least preferred way of all the three cases. Why? Because it is not very easy to bend rebars and use. Okay, so that's why it is the least desirable cases, and is generally only used when there is high shear. Then there are the chances of shear failure is very high. Then only we use uh, such kind of solution against shear failure. Okay, now, so one thing was common in all of these, that we are arresting shear by providing a reinforcement along the cross section length of the section which is in the direction of external force, while failure is arrested by providing rebar at the bottom at the top only. Okay, so shear crack is arrested by providing rebars along the section, and flexural failure is arrested by providing rebars at the top and the bottom of the section. Okay, so now how we design these stirrups? So for that we need to look at stress diagram first. So we said that the shear force at any section is equal to the rate of change of bending moment. That is the thing that we started with at the start. Okay, now for plain concrete we can see this is how normally the stress will vary. And since my shear stress is since the bending moment is minimum at the neutral axis and maximum at the edges, my profile will look like this. Okay, but in case of reinforced concrete, what will happen? My stress profile is something like this. Okay, so here my bending moment is maximum, here it is zero. Here there we say that no stress is acting, all the stress is taken up by the reinforcement only. Okay, so my shear profile for this case will look like this. Okay, so it will increase till the neutral axis and it will stay constant then. Okay, so for reinforced concrete, my shear profile looks like this. Now, since it is difficult to solve such complex stress strain diagram for shear profile, what IS code does, it says that we can go ahead by designing for normal nominal shear stress. So how this nominal shear stress is given. So for a beam having a uniform depth, nominal shear stress is given by this formula: tau v is equal to vu upon d into d, where vu is the shear force acting due to design load. So we know some loading which is acting on a section, that from that load we can calculate the shear force. B is the breadth of the member. For flange section it is taken as the breadth of the web, and D is the effective depth. Okay. Now sometimes we don't know the value of D. So how to start? Whether we should assume capital D or small d? So it is always preferred to assume capital D, because in the end we need to design for the total depth only. So assume some whole number of capital D, assume a cover, assume a rebar dia, and calculate small d. So if your small d is coming out to be a value like 655 or 650 or something also, it won't be a problem, because it is just required for designing. But for actual construction we need capital D only. So it is always preferred to go with capital D before, if it is not given in the question. Okay. So now this is the shear stress that is acting due to external load. Okay, so here we calculated tau v. Tau v was the shear stress which was acting due to external load. Now, what is the shear strength of a reinforced concrete? So the shear force exerted due to external load can be resisted by combination of both steel and concrete. So in flexural failure, we saw that the tensile stress can be only resisted by steel, and the compression stress is resisted by concrete. But when we talk about shear failure, the shear force that is exerted by the external load can be resisted by both combination of steel and concrete. So, in order to design stirrups for as shear reinforcement, we first need to know the shear strength of concrete. How much concrete will resist? So, if we know the shear strength of concrete, say VC, we can calculate how much shear strength the steel needs to resist. And if we know how much shear strength the steel needs to resist, we can design for the required number of stirrups required. Okay. So now, how does concrete resist shear? So concrete can resist shear in three ways: either due to its uncorrect section, due to aggregate interlocking, and due to dowel action of longitudinal reinforcement. Now, separately calculating all these three things, it's difficult. So what IS code says, if we know the area of tensile reinforcement that we have provided for flexural failure, and we know the grade of concrete, we can directly compute the shear strength of concrete by following this table 19 present in IS 456. Okay. So now, once we know the uh, shear strength of concrete, we can, and we know the design shear stress, we can calculate the shear strength that needs to be resisted by steel. Now there is one more clause, that is maximum shear strength of an RC. So just like flexure, where we had limiting value, we used to calculate limiting value, here we have this table. What this table says, according to this, there should be no case in which the shear stress acting on a section should exceed the maximum shear stress capacity. Okay, so for M15 grade it is 2.5, for M20 it is 2.8, for M25 3.1, and it increases as the grade of concrete increases. So if my tau v, the shear stress acting on the reinforced concrete, is more than tau c max, then what we need to do, we need to redesign the structural element first. Okay. How we can redesign? By providing more reinforcement or changing the depth, or the width of the section. Now if my tau v is less than tau c max and tau v is greater than tau c, so my I need to provide shear reinforcement. Okay, and how much shear reinforcement I need to provide? It will be estimated based on the shear strength that the steel needs to resist. So that will be tau v minus tau c. However, there can be a case in which my shear stress is less than the maximum limit, but it is also less than the shear strength of concrete. So here in this case we should not require any shear reinforcement, but code says that we need to provide a nominal reinforcement just for safety purpose. Okay, so now, how to design for shear reinforcement? Once we get which case we belong to, we need to design for shear reinforcement. So this can be done in two parts. What are the two parts? First, we need to know the area of stirrups and we need to know the spacings between stirrups. Okay, so when we design for shear reinforcement, not only the area, the spacing also becomes important because we are running throughout the width of the section. So we should know how much spacing we need
अरे
to
रे रे,
provide.
मेरा बेटा क्लास चल रहा है, चलो रूम में चलते हैं, वहीं तुमको प्यार भी करेंगे.
Can you please mute yourself? Okay, so so where was I? So when we are providing shear reinforcement, there are two parts: area of stirrups that is required and the spacing between the stirrups. So our area of stirrups will be estimated. We can estimate the area of stirrup by just calculating how many number of legs we have in our stirrup and the area of each leg. So generally for shear reinforcement we use 8 mm to 12 mm rebars at stirrups. Okay, so suppose I am going with a two leg stirrup, then my total area of one stirrup will become two times the area of each leg, so 2 times pi r square. Okay, so similarly we can go with 4 leg, 6 leg, respectively. So this is how I will get the area of one stirrup. Okay, and what will be the spacing between the stirrup? The spacing between the stirrup we will calculate how we will see how we calculate that spacing. So that spacing has some clause that is present in the is code. So the spacing between the stirrup should not exceed 0.75 times d, and it should also not exceed more than 300 mm. So these clause we need to check whenever we are designing for shear reinforcement. Okay, now how we calculate the area of stirrups required? So we know how much shear steel needs to resist by calculating the shear force that is need to be resisted by the steel. Okay, so this is tau s times bd. So we will get the shear force that the steel needs to resist. Now this shear force can be equated with the 0.87 Fy ASV d times v SV. How we got this formula? So this is the capacity, the load capacity of our steel. This is the area of steel, and d by sv why we did, so that we can know how many stirrups are cutting a crack. So how to calculate the number of stirrups that are cutting a crack? We calculate by, this is the d depth and this is sv. Okay, spacing between the stirrups. So to calculate the number of stirrups that are required along this depth, we need, and since this is 45 degree, generally we assume the cracking to happen at 45. This will also be d. So number of stirrups required at the spacing of sv we can get simply by d by sv. So now we know vs, we know everything. Area of single stirrup, we know, so we can calculate sv or asv, both we can calculate. Okay, so ASV is the area of single stirrup, okay, that we can fix based on what kind of stirrup we are providing, and we just need to calculate SV, the spacing between the stirrup. Okay. Now, in case of nominal reinforcement, where this is the case, our tau c is greater than tau v, and we should not require any shear reinforcement, we still provide nominal shear reinforcement, minimum shear reinforcement. How we do that? By using this relationship as per IS 456. Okay. So I hope everyone are clear with the relationships that we have talked about right now. Okay, so basically when we used to design for flexure, we used to calculate the area of rebars that we require. But in case of shear, what we do, we fix the area of stirrup. So for a single stirrup, we will know what is the area of that stirrup, and we calculate the spacing between the stirrup. That is more important to us right now. Okay, so let's see the
Sir,
numerical. Yeah,
sir, if tau v is greater than tau c, then we have to design for shear reinforcement also, na?
yeah. And if tau v is less than tau c, what it means that my concrete is enough to resist the shear caused by
Great, great.
external load, but still we provide some minimum reinforcement, some minimum shear reinforcement for safety point of view.
And if sir tau v is greater than tau c, then for calculating ASV, we will use the same formula which you are showing here.
Yeah, if tau v is greater than tau c, it means that the concrete is not enough for resisting the shear force. So we need steel stirrups also for resisting the shear. So how much stirrups we need, we will use these formulas for calculating. Okay.
Yes.
So let's see some numericals now.
Hello,
So
sir.
yeah,
Hello, sir.
yeah, yeah,
Sir, previous slide tau b is greater than tau c max. It also be tau b greater than tau c max. It could redesign the structure elements.
yeah. If my okay, this will be greater.
Previous slide, sir. हाँ वही.
Huh.
Yes, sir.
I think sir we have to redesign the section, na?
Redesign the section means you need to redesign for AST, the area of steel you provided in tension reinforcement or the depth of the section. These all things you need
Yeah.
to redesign until your tau v becomes less than tau c max. Or you can go for a higher grade of no tau grade of concrete you generally don't change. You can change tau v because tau v you calculate how by the force that is acting upon BD. So if you increase the depth of the section, you can reduce the tau v value. So not even AST. By increasing the depth of the section, you can decrease the tau v. Okay.
And what
Okay,
is
sir.
the shear capacity of a beam?
Shear capacity of a beam is given by this only. Like shear capacity of beam, we generally mean how much shear a beam can resist. Okay, so for a reinforced concrete beam, both steel and concrete can provide some shear resistance. So right now what we are doing, we are trying to calculate how we can calculate the shear resistance that is offered by concrete and how much we need to how much stirrups we need to provide for resisting the external shear that is acting. When we will see the numerical now, the things will get more clear. Okay, so just look at this numerical first now. So this numerical says a reinforced cement concrete beam 300 wide and 500 effective depth is subjected to a shear force of 40 kilonewton at the ends. The beam is provided with three rebars of 20 At these are longitudinal reinforcement. Okay, so this is using this you can calculate AST. Design the shear reinforcement for M20 grade concrete. Okay, try to solve this problem. Assume Fe415 grade. When the grade of steel is not given, you can always assume Fe415. I will mute myself for few minutes so that you can solve. Okay, so let's see the solution now. So first of all, what all things are given in the question? So we know width of the beam is 300 mm. Okay. Second, we know effective depth, it is 500 mm. Shear force that is acting due to external load, VU, it is 40 kilonewton. And we also know the area of steel. So what is the area of steel? 3 into pi r square, 3.14 into 10 into 10. So if I will calculate, it will come out to be 942.47 mm square. Okay. We also know we have provided M20 grade concrete and Fe 415 steel. Right. Okay. And we need to determine the design for shear reinforcement. So what will be the first step? So first step will be, okay, so I am removing this part now. So my step one will be to determine the nominal shear stress. Since we know the shear force that is acting, we can calculate the nominal shear stress. How to calculate? Tau V is equal to Vu upon Vd. Okay, so it will be 40 into 1000 divided by 300 into 500. So just do the calculation. So it will come out to be 0.26 Newton per mm square. Okay, this is my tau v. Now first is to check with tau c max whether we need to redesign the section or not. How we will estimate tau c max? We know grade of concrete is M20. Okay, so from this table we can see tau c max value is 2.8 Newton per mm square. So my tau c max is 2.8 Newton per mm square. Since my tau v is less than tau c max, we are safe to go ahead. But before moving ahead, we also need tau c. Okay, so this is what we need to calculate first. How we can calculate? By using table 19 of IS 456. So for this, what we need, we know the grade of concrete M20. We need to calculate the percentage of steel reinforcement that is provided. So how much? What is the percentage of steel? Percent of steel we can calculate by AST upon BD whole into 100. So we have calculated AST, we know BD. So it will be 942.47 into 100 divided by 300 into 500. So upon calculation, just round up to 2 decimal point and it will come out to be 0.63%. Okay. Now sometimes you won't get the exact values that are mentioned here. So what you need to do, you need to go for iteration. So for zero point 0.5, you know M20 grade concrete, what was our grade? M20 grade concrete. Okay, so zero point 0.5 in M20 grade concrete, the tau c value is 0.48, and for 0.75 it is 0.56. So we can go for linear interpolation, we can calculate tau c. So how we can calculate? Just simple, y minus y1 is equal to y2 minus y1 upon x2 minus x1 into x minus x1. This is simple mathematics that you can use. So tau c will come out to be 0.48, which was for 0.5 percentage of steel, and 0.56 was for 0.75% of steel. So 0.56 minus 0.48 upon 0.75 minus zero point 0.5 whole into what How much percentage of steel we got? 0.63 minus zero point 0.5. I hope everyone are clear with linear interpolation, basic mathematics. So upon solving this, and let me solve.
Sir, one question.
Yeah.
Sir, we can apply to the multiplying factor design load 1.5 multiply.
Here design load was not given to us. Directly it is given shear force. Okay, if load is given, then we will calculate shear force first and then we will solve the problem. But in this question, directly the shear force that is acting, it is given. So suppose the
Then given the question to the design shear force, then multiply yes or no.
if it is given right now you can assume this as design shear force only, but generally when you need to multiply the that factor 1.5, it is the load factor, not the force factor. So suppose you have given some ultimate load, working load of say 40 kilonewton per meter or something is acting on the beam. Okay, when such cases is given, you need to multiply it by load factor. Okay, that 1.5 is load factor, not force factor. Okay, so when
Okay,
shear
sir.
force is given, assume it as the design shear force only.
Okay, sir.
So this calculation will come out to be 0.52 Newton per mn square. Now just compare these two values. Tau c is 0.52 and tau v is 0.26. So my tau v is less than tau c max and it is less than tau c also. So which case we are belonging to? We are belonging to the case 3 that we saw, na? It was here. My tau v is less than tau c and it is less than tau c max. So since my shear strength of concrete is enough to resist the design shear force, the shear stress that is acting due to the external load, I should not provide any additional reinforcement. But as code says, we need to provide minimum reinforcement. Okay, so this is the case 3 that you guys were asking. So we need to provide for minimum shear reinforcement. How we do that? By following this formula. Okay, I will just copy it here. So by following this formula. Now how I can do this? Let me take one more slide. So we need to provide for minimum shear reinforcement and we know this formula. Okay, so how to proceed now? So what we will do? We will assume first. Assume, let's assume we are providing 6 mm dia 6 mm diameter 2 leg stirrups. Suppose we are providing. This is something that you need to fix. Either ASV or SV, both you can't estimate from a single formula, na. So you need to fix one value so that you can estimate the other values. I am fix always you proceed by fixing the ASV, because for SV you have some codal guidelines that it should not be more than this or less than this or something. So let's fix the number of stirrups, the area of stirrups. So how we can calculate ASV now? So ASV is nothing but 2 times 3.14 into r square into 3 into 3. Okay, so my ASV will come out to be 56.54 mm square. Okay, now we know ASV, we know value of B, and we know Fy. So my SV can be calculated as SV is nothing but zero point 0.4 into Mass will be 0.87 times Fy, which is 0.415 times. One more thing. Generally, when we are talking about stirrups, we don't go for Fe415. We generally assume Fe4250 grade steel. We could right now design for Fe415, but generally Fe250 is used for stirrups because we don't require that much strength in stirrups. Okay, so right now I'm correcting that thing. Let's use Fe250 grade steel for stirrups. Okay, this is what generally it is used. So 0.87 times 250 times 56.54 divided by zero point 0.4 into 300. Okay, so upon solving this, you will get around 102.5 mm, which we can round up to 100 mm. Why? Because it is practically not possible to provide 102.5 mm spacing. So let's round it up to 100 mm. Now what we need to do? We need to check for spacing guidelines as per IS 456. So what IS 456 says, there are two conditions, 1.75D and 300 mm. So it should not exceed 300 mm. So 100 mm is less than 300 mm, and 0.57D it will be 0.557 times 500. So it is 375. So this value is safe to go with. Okay. So final comment will be, provide 6 mm dia, two legged stirrups at the rate 100 mm center to center. So this is how we state the final conclusion. Okay, so this is the solution. Everyone clear with the solution? If yes, let's proceed on to the one more question. Okay, so what this numerical says, a reinforced concrete rectangular beam of size 300 mm cross 500 mm is reinforced with 1500 meter square steel on tension phase and 500 square steel on compression phase. So this is a case of doubly reinforced beam. Okay. The characteristic strength of concrete and steel are 25 MPa and 500 MPa respectively. It is subjected to shear force of 200 kilonewton at working load. So right now also shear force is given directly to you, so you don't need to multiply with any factor. Okay. So now we need to design this for shear reinforcement. Okay, try to solve it on your own. So let's see the solution now. So what it is given in the question. Okay, so we know the size of the beam. B is small b is 300 mm. B since it is given 500 effective, so we can assume that is small d only. Okay, AST is given 1500 mm square and ASC is given 500 mm square, and we know M25 grade concrete and Fe 500 grade steel. Okay, and it is subjected to a shear force of 200 at working load. So my bad what I said in the start of the numerical na, since it is given that the shear force is 200 kilonewton at working load, we know what is our design load. It is load factor times working load. Okay, so someone asked me in the previous question na, whether we need to multiply load factor or not. When in question such statement is given at working load, then we need to multiply load factor to the shear force. But in the previous question, we saw the it was given shear force of 40 kilonewton. It was nothing was mentioned about working load and all. So we can assume that shear force at design shear force only. Here we need to calculate this. Here we need to multiply 1.5 factor in the shear force that is given to get the design shear force. Okay, just omit what I said in the start of the question. Okay, now this is what it is given to us. Okay, so this part ASC, it is of no use for us. Okay, because when we are designing for shear reinforcement, everything that matters to us is the AST part. So ASC, it is just given for confusing. It doesn't add any value to our question right now. Okay, so we will just start with the solution now. So now the problem is very clear. You know B, you know D, you know AST, grade of concrete, you know, design shear force, you know, okay, and grade of steel, you know. So what we'll do, we'll first calculate the tau C max. We can know since we know the grade of concrete. We'll first calculate tau V. We'll calculate tau C. We will check which case we are belonging to, whether we need shear reinforcement or not. If we don't need shear reinforcement, we'll provide the minimum shear reinforcement. If we need shear reinforcement, we will design for the shear reinforcement required. Okay, so let's add a new slide now. Okay, so let's solve ahead. Okay, so first we will calculate, we know VU. Okay, so how we can calculate VU upon VD. So it will come out to be 300 into 1000 divided by 300 into 500. So it will come out to be 2 Newton per mm square. Okay. Now tau C max for M25 grade, it is, if we go back, for M25 grade, tau C max is 3.1. So it is above the limit. So we don't need to redesign the section right now. Okay, now I need to calculate tau C. Okay, so I can calculate tau C, percentage area of steel. Percent of steel, it is nothing but AST upon BD into 100. So it will come out to be 1500 divided by 300 into 500 whole into 100. So this value, if you will see, it is nothing but 1% only. Okay. So for 1% steel and M25 grade concrete, my tau C is, if we look in this table, 1% steel and M25 grade concrete, my tau C value is 0.64. Okay, Newton per ml square. So in this case, my tau C is less than tau V is less than tau C max. So now we need to provide shear reinforcement. So how we will provide shear reinforcement? By just calculating using this formula. Okay, where was that? Okay, using these three formulas. So first we'll estimate VUS. So how we'll calculate this? This will be nothing but 2 minus 0.64 times 300 times 500. So it will come out to be 204 kilometer. Huh. Okay, my VS will come out to be this, and just I need to equate my VS to, so my VS I will equate to 0.87 Fy ASV D upon SV. Okay, so let's assume we are providing, this time we are providing 8 mm diameter stirrups, 8 mm diameter 2 leg stirrups. Okay, so we can calculate ASV, and once we calculate ASV, we can calculate SV. Okay, I'm just writing the final solution since we need to see a lot, a couple of more numericals, and we won't have time. So upon solving, you will get SV equal to 107.4 mm. You can round up it to 1110 mm or even 150 mm. You can go. Just round up to a higher value always. Okay. Now when you will check this value with the criteria 0.75 D and 300, it will be lower than those two values only. So you will see that this is safe to go with. So finally you will say we need to provide 8 mm diameter 2 leg stirrup at the spacing of 150 mm center to center. Okay, clear with the solution? If no doubts, I will proceed ahead now. Okay, so let's see the next part now. So now we discussed earlier that there can be inclined stirrups also. Okay. So suppose a crack is running diagonally at an angle alpha. Suppose this angle is alpha, and I need to provide inclined stirrups at an angle beta. Okay. Okay, this is alpha, and suppose the crack is running at an angle beta. Okay, so how will be my spacing between two cracks? So it will be calculated by this formula. How this formula came? So this is top reinforcement, which is at a cover of d dash, and this whole depth is d. Okay, so I know this length. Okay, so this length I can calculate by taking cot alpha will be nothing by, if this is beta and this is alpha. Okay, so I can calculate this total length by using the cot trigonometric action. So dc will be nothing but d dash minus d. This is my d dash minus d. So this is d dash minus d cot beta, and this is d dash minus d cot alpha. So this is like the total length spacing between two cracks that we can say. Okay, and the number of effective rebar in a particular region, how we can say spacing between crack upon spacing between the reinforcement. So just when we got the number of effective rebar, we can calculate the shear stress again. Now this times what we need to do, since it is inclined at an angle alpha, we need to calculate the effective shear. So effective shear is calculated by just calculating the shear set with respect to the vertical shear. So for that, sine alpha is multiplied, and then total shear was calculated. How much total shear it needs to resist was calculated. Okay, so these cases are very less, like you will find minimal cases when you need to go for inclined stirrups. So that's why I'm not going into deep, but you can just understand how the designing is done. First you need to calculate the spacing, then need to know the number, then you need to know the maximum shear, and the final formula will be the same then. Okay, so here what they assumed in is 456, they assumed this crack beta to be 45 degree, and they simplified the question. So here you can see there is only alpha, no beta. So beta was assumed as 45 degree. Okay, so this is how stirrups is designed, inclined stirrups is designed. Now equating this to actual shear that we need to resist, we can calculate the spacing between the stirrups for a known or assumed diameter of stirrups. Okay, apart from this, suppose my depth of the section is varying. So this was the last case that we saw in the NPTEL section. Suppose my depth of the section is varying, so how to calculate how much shear stress is acting at a particular section? Now, so this is a basic structural part. Suppose I have a cantilever beam, okay, in which there is some force acting here. Okay, so due to this force, how will be my moment diagram look like? Like this. Okay, moment here will be PL if I assume this is the length. Okay, so we can say how we can calculate at any section what will be the moment, we can easily calculate. Suppose this is X, so here moment will be Px. Okay, P times X. Now suppose first case is my bending moment is increasing in the direction of increasing depth. So suppose my beam is like this. Okay, this depth is D dash and this depth is D. Okay, I'm showing this view only. My beam is like this. Here you can see the top view, I guess. You can say this is the top view or the side view, and you can say this is one more side view. Okay, so suppose I want to calculate what is the shear force acting at this section. Okay, so how we can do? By using this formula. Okay, earlier we saw, we only said v is equal to vw. Vw is nothing but p. Okay, the shear force acting at the end. Okay, now how the shear force is changing with the depth, that we can calculate by calculating using this formula. So here 10 beta is nothing but this angle beta. M will be moment at this section, and D is the depth of this section. Okay, so here my M will be 0, so my formula will become V is equal to VW only. But as I the depth will increase, my shear force acting will decrease, which should occur. Okay, And similar is the case this case where my depth of the section is decreasing in the direction of increasing bending moment, so the plus sign will come in between. That is very common, you can understand, as the more will be the depth, less will be the shear force acting on the member. Okay, so these are simple formulas that we saw in the class in the last live session. We won't see numerical on these, but it is just to clarify what was discussed. Okay, so let's see some more numericals now, some more variation in numerical. So this is numerical for a RC beam of span 6.5 meter is 300 mm wide and 750 mm deep to the center of tensile reinforcement, which consists of six rebars of 20 mm diameter. The beam carries a load of 45 kilonewton per meter, including its weight. Design the shear reinforcement if 50% of the tensile reinforcement is curtailed near the support. Use M20 concrete and Fe415 steel. Okay, so this is one more variation in which the generally design of shear reinforcement is asked. So just try it on your own. Else I will tell the solution. Thank you, Linus. Okay, so let's see the solution now. So what all things are given in the question? I will proceed fast with this question since most of the thing are repetition only. So given is, we know L, we know B, we know D. Okay, and we know AST. Total AST, I will say. Okay, so total AST we know. So it is 6 rebars of 20 mm diameter. So 6 into 3.14 into 100. So it will come out to be 1884.95 mm square. Okay, and we know load acting. So 45 kilonewton per meter. Until it is given that it is working load, you need to assume that it is design load. So right now I am assuming this as design load only. Okay, or you can assume working load only, also that is upon you. Okay, now it is given in the question 50% of tensile reinforcement is curtailed. So what this means, that we only need to consider remaining 50% for designing shear. So this is something that code says, that the curtailed reinforcement is not considered for shear design. So only the remaining 50% is considered for designing for shear. Okay, so actually the area of stirrup that I have, AST dash, is 0.5 times 1884.95, so it is 942 mm approximately. Okay, so this we know. So from AST you can get tau c, and from M20 you can get tau c max. Okay, what we need to get right now? Tau v. So we'll get tau v. Maximum shear force we can calculate since we know the load. So it is nothing but WL by 2. So it is 45 into 6.5 by 2, and it will come out to be 146.25 kilonewton. So tau v is nothing but 146.25 into 1000 divided by BD. So 300 into 750. Okay, so this will come out to be 0.65 Newton per mm square. Okay, so we know tau v is this. Tau c, when you will calculate, it will come out to be 0.27 Newton per mm square. Okay, and tau c max for M20 grade concrete, we know it is 1.8 Newton per mm square. So this is again case 2. My tau v is more than my tau c but less than tau c max. So I will define, I will need to provide shear reinforcement, and Vs we can calculate easily. So that part I am not repeating, it is just simple calculation. So I am telling the final solution right now. You can do the calculation on your own. So I have provided 8 mm dia, 2 lakh stirrups at the rate 250 mm center to center. Here the spacing can be different. The limiting value was coming out to be around 205. So I've chosen 250 mm. Okay. So just remember this part. When the curtailment is provided, we need to also like update the reinforcing area that we are considering for calculating tau c. Okay. And design load is given, so we calculated maximum shear force that will be acting in the middle. Okay. So this is how this will solve. Now just look at the last numerical. A rectangular beam is to be simply supported on supports of 230 mm width. A clear span of beam is given 6 meter. The beam is to have a width of 300 mm. The characteristic superimposed load of 12 kilonewton per meter is given. Using M20 grade concrete and Fe415 steel, we need to design the beam. So this is a complete design question for a reinforcing steel beam, reinforced concrete beam. So some part of this question we have seen in the last class also, in the last live session. So you, if you remember, in the week 3 of live session, we saw the same question where we designed the beam for flexure only. So you need to proceed ahead with that part only. So what you need to do, I will just quickly tell you what we discussed in the last class. So we know beam is simply supported on the width of 230 mm. Clear span is given. So what we did, we first calculated the effective span. Okay, and the depth was not given, so that we assumed 400. We calculated the effective span, it came out to be 6.23 mm. Superimposed load was given, we calculated self load, so we got the total load. Then we calculated the factored load by multiplying the factor of 1.5, and we calculated the bending moment. For bending moment, we calculated the area of reinforcement bar required. Okay, now here in our question, what we need to do, for this factored load, we will calculate the shear force also. How we'll calculate the shear force? So maximum shear force we will calculate as WL by 2. So it will be, what is the load that we got? 23.06 into L 6.23 divided by 2. Just do the calculation. So it will come out to be 71.832 kilonewton. Okay. So in the last class, we saw the flexure design for this part. Okay. Now we'll see the shear design. So nominal shear stress we can calculate. Nominal shear stress will be nothing but tau V. It is nothing but Vu upon Vd. So Vu upon Vd, it will come out to be 0.598 Newton per mm square. Okay. Now we know percentage of reinforcement bar, it is nothing but AST into 100 upon BD. So we know AST, we know B, we know D. So it will come out to be 0.785%. Okay. And since the grade of concrete is given as M20, we can calculate tau C. It will come out to be 0.5864 Newton per mm square. And my tau C max, I know it is 1.8 Newton per mm square. So again, my tau V is more than tau C, and tau V is less than tau C max. So I need to design for shear reinforcement. So that thing is again a repetition. We know how to design for that. So I will tell the final solution. You can try it on your own. So it will come out to be 8 mm dia, two-legged stirrups at the spacing of 150 mm center to center. Okay, you can do this calculation, you will get the similar value. This will be 300 mm. Okay, so this was a complete question. The first half of that question we saw in the last discussion session till the flexure design. From flexure design, we will get the area of steel. Now, once we know the area of steel, maximum shear we can calculate from the load. Nominal shear we can easily calculate. We know the area of steel, so we can calculate percentage reinforcement, and then we can calculate tau c. We know tau c max, so we know which case we are belonging to, and we can easily calculate the shear reinforcement details. Okay, so this was the question. Try it on your own, you will get the similar solution. So just concluding this week, We first discussed design of length section where we saw one numerical. Then we discussed about limit state of collapse in shear where we first saw difference between shear and flexural failure. Then we saw how cracking occurs in shear, how stirrups can be provided and designed. And at the end, we discussed some additional cases like inclined stirrup design and what if the depth of the section is varying. And we saw a total of 5 numericals. Okay, so I hope everyone are clear with whatever we discussed in the session. Thank you. If you have any doubts, you can ask, else we will close the session.